Assalamu alaikum dear students. In the topic of discrete circuit BJT amplifiers, we were discussing common emitter amplifier with an emitter resistance. And we said that when we have an emitter resistance, then it would be better to use T model. But pi model can still be used. So this time I am going to revise previous example of common emitter amplifier with an emitter resistance, but this time we will be solving it by pi model. So we have done all these things right in our previous lecture, but this time we are going to analyze common emitter amplifier with an emitter resistance, but by solving it with pi model. We have seen that we could be having an emitter amplifier, a common emitter amplifier without an emitter resistance. We have solved it by using pi model. We know that we could be having a common emitter amplifier with a discrete emitter resistance, right? And it is called a common emitter amplifier with emitter resistance, and we have solved it by using T model. This time we are going to solve this again, obviously only the AC part because the DC part would be the same. So we are solving here the AC part of this amplifier with pi model, right? Recommended is you have to use T model, but if you want to use pi model, you have to be very careful while taking the emitter resistance, the discrete emitter resistance. And another common emitter amplifier, this one we have already discussed in detail, that we can have better performance, better gain, and better beta stability by having this kind of common emitter amplifier in which we have emitter resistance but bypassed for AC, right? And this is your assignment, right? Actually, this was your assignment. You already would have submitted. So let's analyze this one. Same problem statement, right? Done previously with emitter resistance, same problem, but this time we are going to analyze it with pi model, right? So this was the DC equivalent circuit. Open all the capacitors, you got this one, then Thevenized here, you got this one, you got RB and VPB. This was the DC analysis and Q point methodology, finding methodology. So this one, your IC, this one was your VCE. So this is your Q point at the output load line, right? And at the input load line, you would be having this Q point. And about the AC equivalent circuit and its parameter, shortening all the capacitors, shortening all the DC sources to ground, we had found this one, right? And by taking a parallel combination of these two resistances, we had found this one, right? And by replacing this transistor with its equivalent model, so we said that with RE, discrete RE, it is better to use T model, right? And did we took it, we solved all these things by connecting other discrete components at the base emitter and collector. We have found the required parameters present in this model. Now what we are going to do, we are going to take the same AC equivalent circuit. This one is same, right? But now we are going to replace this transistor with its pi model, right? And let's analyze it. Place the discrete components in this circuit with the model of this transistor. So this is the model. So besides this, we are using this one, and other things need to be connected as it is. So at the collector side, you have collector resistance, discrete collector resistance, and the load. Capacitor is shorted, right? And at the base, you have RB to ground and R signal, right? So here we have AC model parameters. We have to find it GM R naught. Do we need to find RE? No, because here R pi is available, is present. So we have to find R pi. So R pi is this one, right? So this is our stage. Actually, this was our stage. So, but with pi model, this would be our stage. Now to find the desired gain relation and their numerical values, we have to see what would be the input resistances, output resistances, input voltage and output voltage. So when we are, because we are going to see through base, because input is coupled into the base, so our input resistance while looking into the base, once it is found, then we can find Rn, right? And Rn would be equal to Rb parallel to what we have found if we have found Rib. So because this terminal and this terminal are same for the R input base and Rb. About the R out, the output resistance would be looking into the output of the stage. So once we have found all these things, we can relate and found the output voltages, the input voltages, and then the gain from input to the output of the stage, the gain from input to the load of the stage, the gain from input of the sensor or source to the output of the stage, and the overall gain input from the source to the driving load. Let's start with finding R naught. What would be R naught? When we are looking into the transistor at the output of the stage, we can see the RC is there, and RC is parallel to what? R naught. R naught is coming in series with RE, obviously with some relation of I current here and current here. Here is IC, here is IE, right? And but R naught is also parallel to some current source, like, right? Likewise of current source. I want to repeat one thing. Please consider this part at your output, this part at your input. But if we have something here, you have to include this and this. So this will be included here and here as well, right? So what should we do? Because with this R naught, it would be difficult. So as recommended for the same circuit with RE, it is recommended to neglect this R naught, and it is fair because this R naught is very high. Once it is coming in parallel with something, then that parallel thing will be leading while finding the values, right? So let's neglect the R naught, the early effect. So problem become more simple when we are looking into the base, into the output of the stage. Then R naught is looking to be RC only because this current only flowing here, right? So this is your output terminal. So RC is 5 kilo ohm, so this would be your R naught. And when you are looking into the base, you can see you have R pi because you are looking into the base. At the base, you have R pi directly, but this R pi is in series with RE. But R pi has current IB and RE has current IE. So these are in series, but with a factor of, what is the factor of base current to emitter current? Is 1 plus beta. So this RE is feeling 1 plus beta time at the base, right? Because IE is 1 plus beta time greater than IB. I have explained it previously, right? So here we can see you have R pi in series with 1 plus beta time RE. So this is your RIB. And if this is your RIB, then R in will be the parallel combination of R capital B and R input base, this one. So R capital B and parallel to R input at the base, right? So we have found this because this is 3K This is 300, so 301 and 3k is 900 and something k, and when we add 4.45k, right? So we found RIB is 908.45 kilo ohm, and when we try to find 908.45 kilo ohm with RB 33.3 kilo ohm, the parallel combination of these two resistances comes out to be, because this would be leading, right, while finding the value of the parallel combination, because this resistance is very high. So it's the same as found with T model. How? Because we cannot see a similarity here. Abstractly we cannot see, but in detail we can see, right? R pi plus 1 plus beta time RE. This is RIB, right? Let's play with it to see whether we can find a relation of input at the base for the same amplifier. Input at the base while using pi model, and input at the base, resistance input at the base while we had used T model. So we know that R pi is equal to 1 plus beta time RE, input resistance at the emitter, right? So we can plug it here, 1 plus beta time RE, and we can now take this 1 plus beta common. We got 1 plus beta times RE plus RE, which is equivalent to what found with T model, right? So it means these are equivalent because these models are same, are equivalent, but easy to be used for RE or without RE, right? Pi is better when you don't have an RE. T is better to be used when you have RE, because here you can see you may take wrongly RIB as R pi plus RE, right? Because RE is coming in series with small RE, and that is totally is multiplied by 1 plus beta to be seen here in T model, right? So we we have proved it previously, right? And by using this relation we have seen that pi model and T model are equal, right? So let's find the relations. V naught without RL is this one, you already know that. V naught with RL would be this one, R naught parallel to RL. Input at the stage is the voltage developing across input as compared to this one, right? So your input is Rin divided by R signal plus Rin into V signal, as did previously, right? But how about VBE? Because VBE would be a part of this Vin. Vin will be equal to RB, will be developing across RB and its parallel resistance RIB. But RIB having same voltage, but part of this voltage will be appearing at VBE. So we have to find this, right? So V input is further divided into these series resistances, right? So VBE directly have a relation of V signal with this appearance, right? So now we already know without RL is this one. By putting the value of VBE, right, in relation with VI, because you have to find the relation from here to here, we are finding the relation for AV naught. So when we bring VI down, we got this one. This is nothing but AV naught. So this is your AV naught. When we put all the values, we have found this one. And when using the same relation here without RL, we are going to find GV naught to compare it with our previous finding. So we got this relation because we put the value of VBE to be related directly to V signal. This is the one. When we bring this V signal down, we actually finding the relation of GV naught, right? When we put all these values, we have found this one, and luckily these are the same values as found with T model, because there the relation is equivalent to this one because the relation there with RE is equivalent to this relation, right?